Okay, here we go with example problem number 3. Reaction, z goes to q plus t, is shown to be zero order in z. Hey, we got a zero order one. And have a rate constant of, gives us the rate constant, and it's at 25 degrees Celsius. The important part is that the temperature stays the same, because remember, if the temperature changes, the rate constant can change. That's one of the ways that you speed up a reaction, is by having a faster or a bigger rate constant. An experiment was run at 25 degrees Celsius where Z original is, so that's our original concentration. First of all, letter A, very similar to the other ones we've done, write the integrated rate law equation for this reaction. So get your cheat sheet out right here, 0th order, here is the integrated rate law right here for a 0th order. Always use the y equals mx plus b1, and so A at some time is equal to negative kt plus A, and then it's original right here. Then letter B says calculate the half-life for this reaction. So here's our half-life equation for a 0th order. T1/2 is equal to A original divided by 2K. And so the original amount right here, Z original, I used A again when I probably should have used Z. So this should be a Z, this should be a Z, and these should be Z's too. I apologize for that. I'm just not looking at the reactant right here. So anyway, the original amount of Z is 0.75 molar, and then divided by 2 times K, and it tells us that the rate constant is 0.5, and they put it in a fancy way, mole per liter right here, but that is 0.5 molarity. Okay. And then we're going to have to divide those two animals right here. There should be a seconds or a units in here. Let's see if they have any times in here. Seconds right here. This should be a molarity per second as well for that rate constant. Must just be missing that one. So anyway, 0.75, and then divide it by 2, enter, and then we'll divide that by 0.5, and I end up with 0.75. So, oh, that makes sense. 2 times 1/2 is just 1. So 0.75, could have done that without a calculator, and that would be seconds for our half-life time. And then letter C, the last one, calculate the concentration of Q after a time has elapsed. So they throw us a little curveball here. They don't ask us for time like they did in the other two. This time they ask us for a concentration after a time has elapsed. So we're going to have to use time right here again in the integrated rate law, but they're going to ask us for this concentration after that time has elapsed right here. So let's write down that integrated rate law equation. I'll see if I can do it correctly this time. Would be concentration of Z at some particular time is equal to negative KT plus the concentration of Z original. All right. Now they tell us a time right here. We have an original right here, and we're going to look for this guy, so it's actually an easy one to solve for. So this is equal to negative, and then the K, they give us the rate constant up here is 0.5. And then the time, of course, is this number they give us in the problem, 5 times 10 to the negative 3rd seconds. Ooh, not a lot of seconds elapsed. And then plus the original amount right here. So Z original is 0.75. All right, you notice that we should end up with molarity right here as our units. We're adding those two together, so our seconds cancel with our seconds. Let's try this on our calculator right here. So we have 0.5 times 5, enter exponent, negative 3rd. And remember, there's a minus sign right here, so this is going to be a negative number when I write it down. So I end up with 0.0025, negative 0.0025, and then I'm going to add that to 0.75. And we're not going to see a whole lot of change right here, but I'll put in a negative sign, second answer, plus our 0.75, and so we see that it goes to 0.7475. 0.7475, and the units on that are molarity. That would be our concentration after that little bit of time has gone by in a 0th order process. All right, so you've seen examples of a 1st order, a 2nd order, and a 0th order problem. Identify what order the reaction is, find your set of equations, and then go to work on each one of them. Good luck with your integrated rate law problems.